Hi, we are Group 1 and today we are going to present the design and simulation of a centrifugal pump. Centrifugal pumps are a type of hydraulic pumps that transform mechanical energy into kinetic energy or pressure to a fluid. These pumps are widely used in diverse industries, and they are commonly used for pumping liquids in general and allow large quantities of water to be moved. Taking this into account, the demand for more efficient and reliable pumps has increased, and computational fluid dynamics has become an invaluable tool for pump design and optimization. CFD enable accurate predictions of pump performance, cavitational behavior, and flow characteristics, providing engineers with deep insights into the underlying flow physics. Also, the turbomachinery CFD methods transform from a purely academic pursuit into an essential industrial tool. In terms of the state of art, we have the CFD simulation in centrifugal pumps. Some authors review that the CFD application in these pumps show effectiveness in predicting flow patterns, pressure distribution, and efficiency, and others have used the CFD to optimize impeller geography and improving the pump efficiency. In terms of the viscous flow pumping, other authors use CFD to study the impact of viscosity on a multi-stage electric submersive pumps, and Valdez compared pump performance with Newtonian and non-Newtonian fluids, finding that shear thinning fluids can enhance pump efficiency compared to Newtonian fluids of similar viscosity. For the cavitational modeling, some authors use a mixture model with a cavitational submodel to predict cavitation patterns in centrifugal pumps, validating their results experimentally. Others employ CFD to study how blade leading edges geometry affect cavitational performance and propose optimized designs to delay cavitation on set. Finally, for the turbulence modeling, some authors compare different turbulence models for centrifugal pump simulation, and they conclude that the SST model provides the best overall performance in predicting pump characteristics.
The hydraulic design calculations were made using the application Excel, where in Table 1 it can be seen the different parameters that were later used when creating the geometry of the pump. It's important to highlight that taking into account the pump's specific speed, the impeller has an actual geometry which places certain restrictions over the geometry. In order to calculate the velocity triangle, it was defined and assumed that the inlet blade angle had a value of 15 degrees. Also, it should be noted that the outlet diameter was a manufacturer's restriction. The geometric design or CAD model was made using the application Autodesk Inventor 2024. As it is seen in Figure 1, it shows the dimensions of the pump, which was divided in the impeller, the volute, and the assembly of the two. The geometric design was imported to the application Star CMM version 19 in order to create the mesh and realize the different simulations. In order to guarantee the accuracy of the results, a mesh independence test was made, where the normal mesh was with a base size of 1 centimeter was varied 30% in order to evaluate the mesh thinness or coarseness relationship with the accuracy of the results as well as the computational time. According to Figure 2, it was determined that the normal mesh was the best since it offered a good balance between the accuracy of the results in comparison with the manufacturer's data and the computational time. In addition, the normal mesh guaranteed as well a Wally plus less than 5, which allows the mesh to resolve the viscous sublayer directly, creating a more precise flow behavior prediction. Therefore, the normal mesh was used in order to start simulating the pump's operation. The mesh models we use are seen in the screen, and in Table 3, it shows the different parameters used to create the mesh. In Figure 3, the mesh can be seen in different critical parts of the pump, such as the blade, the impeller, the cut water, and the different nozzles. In order to start the simulation process, it was essential to find the Reynolds numbers for both water and mineral oil to identify the regimes of both fluids, and therefore choose the appropriate models to simulate the operation of the pump. According to Table 4, it can be seen that both the water and mineral oil have high Reynolds numbers, and since they are both greater than 2 multiplied by 10 to the fifth power, the fluids can be considered as turbulent. Even though there are different models for turbulent flow, such as the SSTK omega model mentioned before, the K epsilon model was chosen taking into account its robustness and computational efficiency, especially for high Reynolds numbers flows. The K epsilon model is particularly effective for flows with a strong curvature and rotation, such as swirling flows, which are seen within the impeller of a centrifugal pump. Some assumptions for the simulations were that the turbulent viscosity is the same in all directions, that is a single phase isothermal and incompressible flow, and that the system is within a steady state. Regarding the initial conditions defined for the simulations, the initial velocity and pressure were determined in order to ensure that the simulation captures the development of flow from a rest state. In the case of the boundary conditions, it was divided in three different zones: the inlet, the outlet, and the rotation parts. For the inlet, it was defined as a mass flow inlet. The outlet was defined as a condition of pressure, and the rotating part, the impeller, was defined as a moving reference frame in the z-axis. These conditions are essential for ensuring that the simulation results are reliable and applicable to real-world scenarios, providing insights into the system performance and behavior under specified conditions.
In Figure 4, the pump cores for both water and mineral oil are presented. A comparison between the CFD results and the manufacturer's data reveals a noticeable difference in the behavior. Although the pump was originally designed as a radial pump, after running the simulation and recalculating the specific speed using the new data from the best efficiency point, the specific speed increased from 18.41 to 23.21. This shift suggests that the pump's characteristics are more consistent with those of a mixed flow pump, which exhibit similar behavior in the total head versus flow analysis. Figure 5 shows the efficiency curves for water, both CFD and manufacturer's data, and oil. It is evident that the best efficiency point BEP occurs at a lower flow rate for oil compared to water, consistent with the findings reported by Valdez. This difference is primarily attributed to the increased frictional losses caused by the higher viscosity of oil. The higher viscosity creates greater resistance to flow, shifting the VEP to lower flow rates. Furthermore, these increased frictional losses lead to a reduction in overall efficiency, a typical outcome when pumping more viscous fluids. In order to compare the results obtained from CFD with experimental data provided by the manufacturer, Figure 6 was constructed. In this figure, the alternative lines represent the minimum square error for each parameter. The errors were relatively high, with values of 21% for total head and 22% for efficiency. The primary reasons for these discrepancies are linked to the fact that the pump design has deviated from the original manufacturer design due to changes in its best operating point, as mentioned before. Additionally, another contributing factor is the limitations of CFD, which, as previously mentioned, relies on assumptions such as steady flow and neglects mechanical losses related to the motor, including frictions and heat dissipation.
Now, it is worth carrying out a comparative analysis between the velocity profiles for the two fluids that we were working with. Firstly, it can be seen that when the flow rate is zero, all the energy that the pump supplies to the fluid is manifested as pressure in the stagnant fluid. That means that even though there's no fluid movement, the pump continues to transfer energy to the fluid particles trapped in the impeller, which generates a maximum head value within both systems. If we continue to go through the different flow rates, it becomes interesting to note that although the length of the discharge was extended in order to avoid volumetric losses, at low flow rates, backflow phenomena can naturally occur, as in the case of the flow of 90 cubic meters per hour. And eventually, when reaching the best efficiency point, one can see that the magnitude of the velocity increases, and this suggests in real-world applications that the possibility of facing, for example, higher friction losses and even higher risk of cavitation in high-speed zones. On the other hand, these pressure profiles suggest that more pressure is required to move mineral oil than water throughout the pump in order to keep the desired flow rate. This is physically consistent since oil is more viscous than water and therefore it offers a greater opposition to the movement. Now let's take a look at the cavitation. For this analysis, vapor pressures at 20 degrees Celsius were collected from literature. And they are presented on the slide. Since water is more volatile, it is expected to face more cavitation problems with that fluid. One can also see that for both fluids, the greater the flow rate, the more cavitation zones there are. And this follows Bernoulli's principle. When velocity increases, pressure decreases, getting sometimes dangerously under the vapor pressure limit. Let's compare now side by side worldwide plus performance at the best efficiency point for each fluid. On the left-hand side, one can notice that there are barely orange or red values, and the average worldwide plus for the water is equal to 1.4511. And on the right-hand side, worldwide plus appears to be very low with the naked eye. It seems that there are only blue zones, and indeed, the average value for the oil here is low. It is 0.0701. Turbulence models often require low Y plus values. In this case, Y plus smaller than 1 is preferred in order to correctly capture velocity gradients and near-wall turbulent phenomena without relying on simplified approximations such as wall functions. And despite the fact that water wall Y plus was not less than 1, it was less than 5 and continues to be a small value. Besides, this outcome ended up as expected, since Y plus depends on kinematic viscosity, as it can be seen in the equation on the slides. Oil is more viscous than water, then Y plus must have been smaller for oil compared to water. Let's compare now side by side wall Y plus performance at the best efficiency point for each fluid. On the left-hand side,
In conclusion, it was possible to design and simulate a centrifugal pump with water and mineral oil correctly using a normal mesh. Taking into account the results obtained, it is evident that the design pump has the characteristics of a mixed flow pump and the BEP changes. There was a decrease in pump efficiency with mineral oil due to its higher viscosity. Also, compared to the manufacturer's data, relative high errors were obtained due to the change in the BEP and the limitations of the CFD. In addition, an increase in the velocity magnitudes was observed when increasing the flow rates, and an increase in the total pressure of the pump was observed with the mineral oil, once again due to its higher viscosity. Considering that water is more volatile, greater cavitation was observed in the pump with water. And finally, low worldwide plus values were obtained for both the water and oil pumps, thus achieving fine resolution, capturing viscous effects, and precise details on the flow near the wall.